engineer at Great Western Railway. Very pleased that David has come to the centre today to talk about a fantastic project that I think he's been working on for quite a few years. But I'm really fascinated to learn a little bit more today. So he's going to talk to us about the fast charge battery train trials that he's really been leading. So without further ado, please welcome David to give his talk.
Shall I is this picking up okay, Chris? I'm presuming they can hear remotely. So yes, good evening, everyone. Just let a few more come in. Do you want the lights off? Everyone see that okay? Yeah, fine. Okay. Well, so thank you for having me. I've done this talk a few times to other IMechE groups, so if anyone's seen it before, or some of it before, I do apologise. So I'm going to tell you about the what we call the fast charge battery train trial, which is taking place, if this works, on the West Ealing to Greenford line in West London, not far from here. Get the Elizabeth line out to West Ealing, and you've got this little branch line connecting the central line at one end and the Elizabeth line at the other. It's currently operated by a diesel, two-car diesel unit on behalf of Great Western, or by Great Western. And it was chosen as the location for this trial of a battery train and a charging technology, which I'm going to tell you all about. Principally because it's not a very busy line. It's also double track, and we can interleave the testing of the battery train with the normal service train. So we've been doing that since February this year or March this year. And as a trial of the principally of the technology rather than the Class 230 train, which I'll tell you about, but it sort of ended up this way for several sort of historical reasons. Originally, it was there was a company called Viva Rail who I worked for, who you might have heard of. Originally, Viva Rail was the supplier of the train and the charging system as a supplier to Great Western Railway as the train operator. This is all sponsored by Department for Transport. Viva Rail, Great Western and Network Rail to make this all happen. But then in November 2022, Viva Rail went into administration, and again, prompted by the Department for Transport, who wanted to keep this trial going, the assets, the train, the charging system was all purchased by Great Western on behalf of the DFT, and some of us engineers who work for Viva Rail were picked up by Great Western to carry on with things. So that's where we are today. So it's not a very short, not very long line. It's only, I think, 2.5 miles from end to end. So it's about a 4-mile round trip. The charging system is at West Ealing in the Bay platform. So if you're on the Elizabeth line, you can see it as you go through. And it just basically shuttles up and down all day. And I'm going to explain how that works. The key ingredients to this whole trial is really the people, the train, and the charging system. I'm going to start with the people, because that really is the most important thing about the whole trial. I always like to start these presentations with a bit of a nod to this gentleman, Adrian Shooter, who sadly passed away in about the same time Viva Rail went into administration, December 2022. Adrian is well remembered as the sort of one of the leading figures of privatisation. Took on Chiltern Railways, or took on the part of British Rail which became Chiltern Railways, and totally transformed it with a route modernisation, new trains, new signalling, high line speed, line reopenings, double tracking where there was previously single tracking. Awful lot of good things came out of that. So, by the way, as engineers, have a good read of those 2 books there, because they're fascinating and inspiring. One is Adrian's biography, and the other one is specifically about Chiltern Railways. Anyway, Adrian retired from all that, but didn't retire for very long, and decided that he wanted to do something a bit different. And at the time, there was a gap in the market for diesel trains, and he saw an opportunity which no one else did, which was to take old underground trains and repurpose them as diesel electric multiple units. So the train that you see there, or standing just behind Adrian, is one of the old District Line D78 trains, which have now been replaced by the S-Stock. But they were otherwise going for scrap, but they weren't too bad actually. They were aluminium bodied. They'd had an interior refresh sort of 5 or 6 years previously, and they'd had new bogies about 15 years previously. I think it was that sort of order. So actually, they weren't really ready for the scrapyard. It's just they happened to be going that way because LUL wanted to standardise rolling stock. So I'll come back to that in a minute. The team now, I mean, Viva was a lot of people and achieved a lot of good things, which I'll talk about in a minute. The team now really consists of, there's 9 of us engineers, plus the supporting cast, obviously, within Great Western. We mustn't forget, we've got, it's quite nice actually to have the covering fire, if you like, of a big train operator, because all of a sudden you can just go to the right person to speak to rather than have some sort of, you know, customer supplier relationship. You can go and talk to the ops people, and you can talk to the procurement people and all the rest of it. And actually bringing us in-house like this has been a really positive thing. So we're now still, you know, the core ex-Viva team, plus some others. And the whole project has really sort of brought people together. It's lovely to see. We had an incident where the train was at West Ealing and it got graffitied overnight. It wasn't long after it arrived. And the whole cleaning team came out almost without being asked, you know, to clean it all off, because they were so sort of proud of this project. So it's, you know, it's great to see. And we have some fun as well. This is a quick history of the very rapid evolution of the class, what became the Class 230 product. I won't go into too much detail. Started off with the D78 underground trains. Then it became the first prototype diesel electric unit, which was originally 2-car and then 3-car. So top line, second from the left, that was the prototype diesel electric train. I won't go into all what was done to make it from an underground train into a mainline train. There was a lot of work in that, and it took about 2 or 3 years. But that unit was 230001. Now that is actually the unit that is now our battery train, by a sort of quirk of fate. Along the way, Viva built 3 2-car diesel electric trains for West Midlands Railway, or West Midlands Trains, which ran on the Bedford-Bletchley line. Then it dabbled with battery. The first dabbling with battery was another prototype, 230002, not shown here. But it then took the diesel and the battery and combined with a hybrid unit, and that became the Welsh units, which are 5 times 3-car units. They have batteries on the leading cars and diesel gensets in the middle, and the diesel gensets are essentially range extension for the batteries. So that is a hybrid architecture, and those trains are still running. It's fair to say they weren't very reliable, and they're still struggling with lots of problems. But TfW have invested lots of money, and they're trying to make them good. So they're running between Wrexham and Bidston. Then branched out into third rail electrification for the Isle of Wight, and that's where I got to know Chris. So there's 5 2-car units on the Isle of Wight. Again, I think originally that was when the Isle of Wight infrastructure was renewed. It was looking likely to be battery trains, but for various reasons it wasn't stuck with electrification, and ended up with 5 2-car third rail electric trains. Now that wasn't as simple as you might think. Although the original D78s were electric trains, they were third and fourth rail, and so we had to sort of go around the circle again and end up with a third rail train with a totally different power architecture, and yeah, another sort of branch of the evolution. Just to round the picture off, the original battery unit 230002 went to America, which is the one that's painted orange and black. That guy there in the yellow hive he was Henry Posner. He was the main funder of Viva. He put all the money in, and he's still promoting actually a thing called Pop-Up Metro in the US, which is all about taking old freight lines and sort of introducing a simple passenger service with a battery train. The original idea was a 230, but it could be any type of rolling stock that does a similar job. So that's an interesting thing that's still sort of going on. And then finally, we took the original 230001 diesel units, turned it back into a battery train. Well, not back into, we turned it into a battery train. We took it to the COP26 climate change conference in November 2021, and we ran it as a demonstrator for 2 weeks in and out of Glasgow Central, carrying invited guests. And then finally, that's the train that became the fast charge unit that we have today. Just to say a little bit about what's gone on in the last few years. Viva went bust. We had to get rid of a lot of stuff. Just to say, it's not just been about considering this trial. We had an awful lot of assets to get rid of. So some of them were sold, some of them were scrapped. We had a factory to clear out. So me and my little team weren't just doing the trial. We were also at the same time clearing out the factory. So many dusty hours of sorting, and an awful lot went in the skip, unfortunately. But that's almost a separate story. But that all started in February 2023. Great Western took us on, and we remobilised the team, got ourselves a new office in Leamington Spa, got rid of the factory stuff. By about June, that was clear, so we could then focus on the train. Here's the train. Now, we had to find somewhere to actually recommission it, because it had been stood for about 5 or 6 months, I think, whilst the administration was going on. And it was at Bletchley Depot when that happened. And West Midlands Trains were redeveloping that depot, so they wanted us out. So we had to find a new home to go and recommission the train. So slightly ironically, we ended up back at Long Marston, which is where Viva Rail started in the first place, by which point Porterbrook had purchased Long Marston and the horrible old shed that was covered in. It was a rough old facility when Viva Rail were there. Porterbrook have invested about £10 million in it now, and it looks absolutely wonderful. It's got three roads of pits, proper lighting, proper everything. So we were able to take the train back there and recommission it. We recommissioned every system because we didn't want to take a chance on there being. We didn't want to assume that it was still okay. We wanted to recommission everything, so we did that. Just going back in time a bit, this is what the train looked like in when was it? Early 2021. It had been stood in the field. It had done its work as a diesel unit, and sort of time had moved on, and it had been stood in the field, rotting away. This is at Long Marston again in Warwickshire, and you can see the state of it. It wasn't very pretty, so we had to basically gut it and start again in order to turn it back into battery units. We totally rewired it, rebuilt the cab, refitted it, and in amongst that we had to make some changes as well. Obviously, to make it into a battery train, we took some of the architecture that was there before in its diesel form, but had to do certain things. Now, one of the challenges is, where do you put the batteries? These batteries are not small, and this is the underframe of one of the motor cars. So you've got motor trailer motor car. Now, for various reasons, the batteries, which are the big blue lumps there, 3 of them, they are the same shape and size as the diesel engines were. So again, another story, but we ended up with batteries that were sort of similar fit, form and function as the diesel gensets. But one of the challenges that Adrian had given us, I don't want just 2 of these things, I want 3. I want 3 batteries. So he wanted to absolutely stuff the underframe full of batteries. So we had to find space for the 3rd battery, which meant rearranging some of the other furniture as well. So we had to relocate the main reservoir, and we had to relocate, I don't know what else we had to do at the time, but we only just managed to fit it in, as you can see. And obviously, with each battery weighing 1.7 tons times 3, that's an awful lot of weight on the underframe. Now, thankfully, these trains, when they were underground trains, were designed for heavy crush loading. So they actually had just about enough capacity in the structural strength of the body shell to allow for this. Now, you don't have as many passengers on these trains, so you sort of trade passenger load for battery load. That's kind of what's happened. So we designed all of that, and in amongst not just the moving of the big lumps of furniture, there's an awful lot of, you have to find space for the cables when you're doing batteries and charging. You're talking about pretty thick cables, so actually finding a home for them and finding a route for them was also a bit of a challenge. This is the diagram of where the cables go. Imagine that's the plan view of the underframe. You've got 3 distinctive yellow rectangles representing the batteries, and then the purple lines are where all the cables go. So you've got to take power from the batteries to the traction control unit, which is the brains of the train. You've got to take cables from the pickup shoes for the fast charge system, which I'll explain in a minute, to the battery. So in the end, what we had to do, we had to cut some of the floor out, and put the cables sort of underneath the floor, and then lay the floor back on top of it. So the floor actually supports the cables, as well as being a fire barrier and also being a floor. So it sort of performs 3 functions, and you can just see some of the cross section of that below if you like this sort of detail. And what we ended up with in terms of mass is a 96-ton train, which is about 8 tons more than the equivalent diesel units. So yeah, battery trains are heavier, not surprising there. And you've got a capacity of about 37 tons of passengers, which leads to 133 ton if you really crush loaded it, which on the Greenford branch you're not going to do, but that's the plated weight of the train. This is what it looks like on the inside. It looks like a new train. That was always the intention. So, and we have had lots of positive comments. We had, and we also have it now. people get on and they go, "Oh, this isn't like an underground train at all." You know, it's got new seats, it's got new tables. Well, they're not so new now, but it looks like a new train. And I say that was always the intention of the Class 230 Viva Rail product. It was to make it look and feel like a new train, and sort of you know, confound people's expectations. We've also fitted the old LUL trains used to have a door between the carriages. Now they've got a little gangway. It's not a wide gangway like you see on Elizabeth line, but it's a walk-through gangway, so that's a nice feature. And it's also got draft screens, and it could have luggage racks if you want them as well. So there's all kinds of stuff. This was the train at COP26 at Glasgow Central, and for a bit of publicity, we ran it across the Forth Bridge as well, which was nice because supposedly it was the first ever sort of pure electric train to run over the Forth Bridge, but without electrification. So that was fun. So onto the fast charge system, which is what you've all come to hear about. Obviously, with the battery train, the problem is your range limited. I mean, the average diesel train will go 1,000 miles between refueling, and you just can't do that with a battery train. So you have to find a way of charging it. There's no way you're going to get a driver to get out and plug it in for 20 minutes. That's not going to happen. That's not practical in a railway environment. And there's no way you're going to change the batteries either with some sort of mechanical handling, as someone suggested to me once. Not 1.7 tons, you know, no. So the system that was devised, and I don't actually know who in Viva Rail invented it. There's the opinion is out. I mean, there's different. It wasn't Adrian. It was one of the other electrical engineers. There's a bit of sort of historical competition about who actually was the inventor of the system. But what we've ended up with is a system that automatically charges the train. All the driver has to do is stop it in the right place. And we're not talking about, you know, millimeter tolerance. We're talking about half meter tolerance, average sort of stopping tolerance at a station. And the way it works is like this. The kind of power you need to charge the batteries is quite enormous, and you can't just connect to the national grid and, you know, do that, because there just isn't the capacity to do that. So you have to have a energy buffer between the train and the national grid, and that's where the what we call the fast charge battery bank comes in. The big thing you see in the middle, that is essentially a 20-foot shipping container, which has got some batteries in it and some power electronics, and it trickle charges from the grid when there's no train around. When the train comes in, it connects with the battery bank via some rails in the forefoot, which I'll show you in a minute. They're a bit like third and fourth rail, but they're not, when there's no train around, they're not live. Basically, they're only live when the train is on top of them, and various interlocks have kicked off. And it has shoe gear, again, similar to what you see on the Underground or Southern region, but these shoes are retractable. So most of the time when the train's moving, the shoes are up and well engaged. They only come down when the train is about to stop at the charging location. The shoes come down and the shoes run up the charging rails, train stops, handshaking takes place, and then charging happens. That's a very simple explanation. And with this system, you don't need a very big connection to the grid. As you can see here, it's only a 3-phase 400 volt 63 amp connection, which is sort of a workshop supply. So it's nothing special. Doesn't mean you get a DNO any quicker, a DNO connection any quicker. It still takes a long time to get a DNO connection. But in principle, it's much simpler and cheaper to obtain than it is if you're putting in, say, 25,000 volts, you know, over electrification. So that's the basics of the system. And then here's a little graphic of what it actually looks like, sort of step by step. In the forefoot, you have the charging rails, and you've also got some RFID tags, which are RFID beacons. So if you're familiar with ETCS and that system for signaling, it's exactly the same beacons. They're just programmed with a different code. So they're kind of off-the-shelf beacon technology, and you have 3 of those beacons. One is what we call the station confirmation beacon. So hopefully this will work if I press. A little train will come along. There it comes. So the first beacon says station coming up. So that's what arms the system. The second beacon tells the train to lower the charging shoes. And then once the train has stopped, the third beacon says, I'm in the right place, and charging commence. Now, there's also another layer of interlocking. There's actually some proximity sensors which pick up on the bogey frame once it stops in the right place. So it doesn't just rely on those beacons. it's got a Wi-Fi communication between the train and the battery banks, and it's also got proximity sensors as a final check to make sure it's in the right place. What this does mean is, if any of those things don't pick up properly, then charging just doesn't happen. So, as we're now finding, there's, well, no, that's probably unfair. It is actually proving to be quite a reliable system, but it is a little bit sensitive to, comms dropping out, or, proximity sensor being, knocked over or something like that. But I suppose that's the way it should be, because what we wanted to make sure is that we don't, try and charge the wrong train at the wrong time. That would be terrible. And one of the stipulations of ORR was that if you're going to have rails in the forefoot like this, they can't be live. They can't be live when they're not protected by a train. That was one of the first things that was agreed. Hence this system. Now you'll see that it's got 3 rails. You can just about make out. The middle one is longer than the other 2. The middle one is the positive rail, and it's got yellow guard boards on it. Now it doesn't need those yellow guard boards. That's just Network Rail being a bit sort of over the top. But anyway, we had the yellow guard rails. The 2 either side of it are the negative rails. Now the reason there's 2 is because the shoe gear on the train, there's only 2 shoes, one positive, one negative on the train, and the positive shoe is always in the middle of the train, and the shoe gear is sort of offset from the centre line. So no matter which way around the train comes in, the positive shoe is always in the middle on the positive rail. So there's no need for any clever switching. Now with the 3-car unit we've got, it doesn't actually matter. But if you had a single car unit, you would get that effect. You would end up with the negative shoe going from one side to the other, if you think about the geometry of it. And at West Ealing, you've got 2 sets of rails, 2 fast charge battery banks. Each one serves a driving motor car. So you've got 2 driving motor cars, 2 sets of charge rails, 2 fast charge battery banks, which gives redundancy. And actually today we were charging the train with only one end working because we've got a problem with the fast charge battery bank. But that's great because it means you can still carry on. You just don't charge as fast, but you can still do a full day service on that basis. Right, I'm going to try and talk about power flows now, even though I'm a mechanical engineer, not electrical, but I'll give it my best shot. This diagram explains the elements of the entire system in block form. So you have the grid connection via a cable going into the fast charge battery banks, FCBB. The FCBB has got some from its own hotel load, so it's got its own air conditioning unit to keep the batteries at a stable temperature. And then obviously, but the main power flow is into the batteries themselves in the fast charge battery bank. Then you've got cable coming out the fast charge battery bank going to the charge rails in the forefoot, and then you've got everything on the train. So the train has got the shoe gear, which feeds directly into the traction batteries and also into the auxiliary power supply unit, and it also actually feeds the saloon heating as well. I won't go into too much more of this, but it's sort of standard power architecture for a modern train, really. Now the batteries, which is what everyone's always interested in. For a long time, we were telling people, oh yes, it's lithium iron phosphate batteries, and not long ago, someone said, oh well, how does that compare to lithium titanate? And we said, oh well, I don't really know. They've all got pros and cons, and what you typically find when you look into it is what you're trying to consider is what's that? 8 things. So specific energy and specific power, i.e., how much energy and power you can get per unit mass in your battery, but also how safe the chemistry is, how it performs. So that might be how fast you can charge it or discharge it, how long it's going to last, lifespan, and how much it costs. Now each different chemistry it has a different shape on that spider diagram, depending on you sort of stretch it around and you can see. So what we sought to do is put our chemistry onto one of those spider diagrams so we could compare it to other chemistries. What we found when we started digging into it with the battery supplier, who are called Hoppecker in Germany, is that actually we've got this quite interesting hybrid chemistry, as illustrated here. We've got a lithium titanate anode and a an NMC cathode. Sorry, a cathode that's actually NMC, nickel metal, whatever it's called, LFP, and aluminium foil. So you can't really say this battery is LFP or lithium titanate. It's actually a hybrid of all. And so the answer is, more complicated than we thought. To us, it's kind of just a black box. Up until now, it's just been a black box. You buy the battery, you know how to treat it, you homologate it. But actually, the detail of what's going on inside, we hadn't really got into. But that was an interesting sort of finding. So now we know a bit more about our battery chemistry. Suffice to say, lithium phosphate and lithium titanate are supposed to be some of the safest battery chemistries out there, which is why they've ended up being used on trains and in EVs. This is what the batteries actually look like in the flesh. As I say, they're enormous things. Inside them, they have 3 modules, which is illustrated on the top right picture there. That's a module, and then inside the module is the cells, and the cells are called pouch cells, and they're sort of the shape of an A4, an A4 book. But in between each pouch cell is airflow, and that's how you can manage regulate the temperature so well with this type of battery. So when you're charging, discharging, the key thing is you're generating heat in doing so, and you have to manage that temperature change. Basically, batteries don't like being too hot or too cold. We all know what happens when they get too hot, but when they get too cold, that's not good for them either. So these are very, very actively managed batteries, as opposed to the average e-scooter, obviously, which doesn't have any of this. But this is very actively managed. So each battery raft, as you see here, has got its own little HVAC unit to keep the temperature in check. You monitor things like individual cell voltages, individual cell temperatures, the balance of the cell voltages as well. You monitor all of that. Each battery has its own battery management system, and that all feeds back to the main train computer, TCU. And it all forms part of the safety case as well. So, with lithium-ion or lithium titanate batteries, there's no real chance of putting. If you did get thermal runaway, you can't put them out. So you put all your efforts into stopping it happening in the first place. There's basically 7 things that can lead to thermal runaway of batteries, illustrated on the left of the image here. So, and these are the things that you're trying to prevent. So you could have external heating, you could be getting close to someone else's fire, overcharging, over discharging, charging at too high current, structural damage. So somebody could crush it or put actually crush is noted separately, but structural damage could be somebody firing a bullet through it or something like that. Penetration tests, they have to do all that, and then finally short circuits as well. So all the efforts go into stopping that from happening in the first place. Now, that can either be through the battery management system, or it could be through actual mechanical design. So, these have got a pretty heavy-duty frame around them. So if they did fall off the train and hit the track, they would be pretty resistant they wouldn't get very damaged, I would have thought. They've got internal firewalls. And then as you go, and if all of that fails, you've then got downstream mitigations as well against the effects of thermal runaway. Things like treating the fumes that arise. It's actually got a fume box in it with some clever chemicals in it that is supposed to take away the worst of of any fumes that might arise. So on and so forth. And as you can imagine, it took quite a while to convince the safety authorities to put this on a train. I think VivaRail, we weren't the first to put lithium-ion batteries on a train. I think that went to about 2013 when Bombardier did a Class 379 convert or put some batteries on the Class 379. But we were, I think, probably the first company to put this amount of batteries on one train. So every step along the way, very, very careful scrutiny of all the changes that we've made. It's a similar story for the fast charge battery banks, although you could argue that the risk is not so severe for these because these sit on the track side, and if they did catch fire, it wouldn't affect as many people as it would on a train. But again, they have very active management of the batteries, and in addition to that, this is a slight variant of the previous slide. They actually have their own fire suppression system in them, in the containers. So as you can see, we've done just about everything possible to prevent anything bad happening. Anyway, back to the more fun stuff. This is the development of the shoe gear, and because this had sort of never been anything like this had never been done before. Obviously, there is shoe gear on trains, and we were very conscious of certain things when it comes to designing shoe gear. Now, the first thing is, if you're designing shoe gear for a train, normally it's mounted to a bogie, which is a horrible vibration environment. And I've got some personal experience from a previous job of that sort of, because I was a bogie engineer at Bombardier for a while. And terrible problems designing shoe gear because of the vibration environment. So what I decided to do was our shoe gear, we'd mount it on the body, so that it was in the what they call the secondary sprung environment. In other words, it's the same vibration environment that the passengers feel, which is two stages separated from the track. You know, you've got primary suspension, secondary suspension. That also means that the design of the shoe gear is adaptable for other types of rolling stock. It's much easier to mount it onto another car body than it would be if it was bogie specific design, if you see what I mean. The only thing you have to watch with that is the movement of the shoe gear on curves. So, you know, if you've got overthrow, what they call overthrow, when the carriage goes around a curve, if you put the shoe gear, say, in the middle of the car, you get the worst overthrow and you might end up with the shoes not on the rails. So we put the shoe gear near to the bogie pivot centres so that it suffers less of that. The key to the shoe gear is the shoe itself, which is a carbon copper composite. I never get that right. So that gives you the conductivity, but also allows you to deal with the high currents. So if you were putting the sort of currents, if you're putting 1,000 amps through normal shoe gear, it would probably weld itself to the rail. So these copper carbon composite shoes, which were tried in London Underground and other metro systems, are sort of off the shelf, really. The rest of it was all Viva Rail design. So I mentioned that they're sitting on a frame that allows them to deploy and retract. They deploy downwards using air cylinders, and they also retract upwards using air. They also have springs to pull them back up again if all the air disappears. So if you get a failure mode where there's just enough spring force to pull them back up again. What you've also got to consider with these shoes, you have to maintain a certain pressure between the shoe and the rail, because if you don't have that correct pressure, then you might end up with hot spots because you haven't got the correct contact pressure between the two things. That's also one of the things we monitor when the charging is going on. We actually monitor the pressure on the shoe, and if that starts to go down, then it will stop the charging. It's just one of the many things that will stop charging. So having designed that, worked out where it's going to go, how it's going to be mounted to the Class 230, we then decide, well, how are we going to, structurally analyze this? And some of you might be aware that whenever you bolt something to a train, you have to test it against GMRT 2100, which then refers to another BS EN standard, and you have to subject it to certain proof loads and fatigue loads and vertical and lateral and all the rest of it. Now, the problem is with this shoe gear, there was no sort of precedent for it. So we thought, well, you can go so far with finite element analysis, but ultimately we're going to have to test this for real, because the FE8 people were a bit sort of, how do you simulate this load case? All these load cases associated with deployment and retraction of the shoe gear over many thousands of cycles. So we built this rig, and this is in the backyard at Viva Rail's old Southern factory. It consists, it's a bit Heath Robinson, it consists of two what they call track map trolleys, permanent way trolleys. One of them is tied to the end of the track, or chained down, and the other one moves backwards and forwards, which I'll show you a video of in a minute. The one that moves backwards and forwards has got the shoe gear mounted on it, and it basically just cycles the shoe gear, so the shoes come down, up the rails, retract, back again, and it does that for thousands of cycles, or it did that for thousands of cycles, just to see what effect it had on the mechanics of it. So between the fixed trolley and the moving one is another big air actuator pushing it backwards and forwards, and you can just see the air receiver in the back. And we made it all out of leftover parts, really. So that was very good fun. Let's see if the video. Right, here we go. Also tested it in all weathers. We sought to do this. Obviously, one of the big considerations is, well, what happens if you get ice on the rails, or what if you get leaves on the rails and all that stuff, or get oil on the rails? So the day that we actually created ice using ice from the supermarket, and I think we used nitrogen or something. We called it, super cooled it, packed it around the rails, and then it snowed the night before. So that's where this video comes from. So you can see, hopefully this will start in a minute. Yeah, no. So here comes, shoes come down, run up the rails, push the snow out of the way. I mean, to be fair, that is nice soft snow. And then it retracts, and it just did that for 20,000 cycles, which represented a year of usage. But obviously now with the real train in situ at West Ealing, we're testing the real thing. And strangely enough, the other day we noticed the diesel train was putting oil all over the rails. It was dripping oil all over the rails, and it didn't have any effect on the charging whatsoever, which was nice. So that's that. And oh, that's a repeat. Right, and then this is a video of it when we were at Bletchley Depot. What you see is some short charge rails. Those aren't representative. Well, they are representative, but they're not as full. They're not the full length of the real thing. What I'm going to show you is the sort of trackside view of what happens. The white sheet there, that was just to protect the shoes, because in this particular location we had some concrete, as you can see, and if the shoes had hit the concrete, they would have damaged themselves. So we had this sort of skid pan arrangement just to protect the shoes as they came down. But at West Ealing, you've just got ballast instead of concrete in the middle there, so the shoes don't come into contact with anything. But I'll just play this video, and you can just, I mean, it's not that exciting, but so train comes along. Obviously, the driver has to slow down to a reasonably slow speed for all this to happen. So the first leading bogie passes over. Again, we kept the shoe gear away from the leading bogie because that's where all the antennas are. So we wanted to separate. There they can. So you just see them come down. It's like Wallace and Gromit, and then up the rails, and then it stops. And that's all. That's all you see. It's quite unexciting, really. And then once the charging is finished, as soon as the driver puts the power brake controller into step 1 or power step 1 or whatever it's called, the shoes automatically retract within a sort of half a second, and brakes come off and off you go. So all the driver has to do, stop it in the right place, put it into neutral, put the brake, make sure the brakes are on, and it all happens automatically. The only indication the driver gets, by the way, that anything's happening is a single yellow light in the cab, which is just to indicate that charging is happening. You can also see charging is happening if you step out of the train and look at the body side indicators. They flash white, and that again indicates that charging is happening. But we were quite deliberate about not telling the driver what the state of charge was, because at the moment the driver doesn't know how much diesel they've got. So why should they know how much? The problem is with telling them how much battery they've got is that they start to worry about it, and then you get, I can't go, I can't do the trip, I'll have to take the train out of service. And so there's a bit of debate about what information to give to obviously we monitor the state of charge remotely, and there's a remote monitoring system, and there's alarms if it gets too low and all the rest of it. But the driver is sort of, we don't tell them very much, rightly or wrongly. But actually that's gone down all right with most drivers, so I've shown you that. Okay. I'd probably don't say much about this, really. Well, I'm not going to go into detail, but suffice to say, the approval of all this was hard work for all the right reasons, because obviously we are dealing with high voltage and batteries and a new system, and fundamentally we were working under the common safety method, and the first step of that is to decide whether the change you're making, or to define the change first of all. So put a boundary around what you're actually changing in the railway environment, and then to decide whether it's a significant change or not significant change. Because this is the first time that this charging system had ever been used in the railway, it was deemed to be significant change, which then brings in the need for an assessment body, and a third-party assessment body. So some of this, I think, in light green is all the stuff we had to do for the assessment body. So you have a big hazard identification session, or we have several of them actually, and then you have a safety justification report, hazard record, and a load of safety requirements that come out of that. You then have to close out the safety requirements either through design or through other mitigations or whatever it is. Once you've done all of that, you get your safety justification report, you give it to the assessment body, ASBO, and they assess it, ask lots of questions. You then go back, answer questions, make design changes, whatever it is. And at the end of all that, once everyone's satisfied, you get your SAR, Safety Assessment Report. You give that to Network Rail. 3 committees look at it in Network Rail. And eventually you get something called a DOCOR, which is a Declaration of Control of Risk, which is your sort of passport to liven up the system. Now, that's a very simple version of it. Oh, and on top of that, there's also Great Western's own safety validation process, which is kind of a reflection of all the other parts. So as long as you've done your compatibility work for both the train, and you've got to make sure this, the charging system doesn't set the signals to red, or set off the track axle counters and all that stuff. So you've got to do full set of gauging reports, all that compatibility stuff. You have to do that, and it all comes together at the end with a big tick in the box from Great Western to say, yeah, we're happy. So that all of that started under VivaRail, but then it sort of stopped, obviously, for obvious reasons. And I had to pick it all up again with my colleague Stuart Bauer, and the sort of two of us had to learn how this all works. We'd never done it before, so it was very much a learning curve on the approval side. But we got it approved, and it's now essentially we can use it in an unrestricted fashion. It was several stages towards that, and Network Rail have been involved all the way through. So it was very much a partnership, and we denigrate them, but actually they've been pretty good. But it has been a bit of a tough journey. Back to more interesting things. The other, the question I talked earlier about, battery trains have only got a finite range. So we've got our charging system, but then you have to consider, well, how far will it actually go? Not just under normal conditions where everything's working fine, but under sort of perturbed scenarios where you might have, for example, one of the two trackside battery banks has stopped working, or maybe a couple of batteries on the train are no longer responding or something like that. So you have to consider the effect of that. Now, we were lucky to have a graduate or undergraduate actually come to work for us in VivaRail days for a year-long placement. And he was given the task of developing a model of how this system works. And being young and bright, he took it on and just came up with this wonderful model in Python, which is a coding language which I don't understand. But anyway, he ran with that, and then he went back to university, and we got another one called Jonathan, and he refined the model, improved it, expanded it, all the rest of it. So we now have this wonderful model which we call the Battery Train Network Simulator, BTNS. And you can almost, if you can imagine it, like you can sort of click and drag various elements into it. So you've got a traction motor, you've got the characteristics of the motor, you can click that into the model. You've got a battery that's got some characteristics, you click that in, and you gradually build up the overall model with all these little elements. And of course, the characteristics of each element is, based on data sheets or real life testing or whatever it is. So you can build up this model of the train, which is what these blocks represent here. But you can also build up a model, equally as importantly, of the route that you're running the train on. So you need to know things like, gradients, number of stations, speed limits, driving styles, and all of that. And all of that has an effect on the overall energy consumption of the train. So out of that comes these plots, or plots similar to this. The top left one is showing the green line is the speed profile. So you can see speed goes up, changes a bit, goes down, stops. So you can see the station stops. You've also got the blue line is the total traction battery state of charge, the sort of average state of charge of all 6 batteries on the train. And you can see how that initially goes up, and then it starts to come down. Every time you stop, you use, and start again, you use energy, so that goes down. And then, of course, when you stop at a charging station, the blue line goes back up again. What else have you got there? You've also got distance traveled in red. But crucial to all this is not just to model it mathematically, but to validate that model. And we started validating the model when we ran the train at COP26, and we had 2 weeks of running between Glasgow and Barhead. And actually, the correlation wasn't too bad. So the bottom right plot there, that shows correlation between predicted and actual energy consumption, and it wasn't far off. And this is actually a real plot of what the batteries do. This was what I didn't say is at the moment we're running the train on the Greenfield branch, sort of Tuesdays, Wednesdays, Thursdays, just to give us enough time to sort of set that up for the week and then analyse the data at the end of the week. Unfortunately, we can't run the train. The normal diesel train runs, I think it's 31 round trips a day, 6 days a week, and we can't do that while the diesel train is there because there's not enough paths on the line to do that. So if we want to do a full-on 30 round trips a day, we have to do it on a Sunday. So we did that for the first time in June, Sunday 30th of June, and that's what the graph looked like of battery state of charge. So, and you can see the sawtooth represents, when it goes down, that's energy being used when it's running between West Ealing and Greenford and back, and then when it goes up again, that's where it's being charged. And you can see it's pretty uniform profile all the way through the day, except for about 6 o'clock in the evening, when it didn't quite get a full charge, and that's where there's only a half charge you can just about see, and then the overall state of charge ended up being a bit lower, but actually it was fine. It made it through the day. So actually what we found in testing is that we can do about five round trips comfortably without charging, 6 at a push, but by the 6th one we're getting a bit nervous and we want to take it back to depot. So that shows you there's some resilience in the system for this, if something goes wrong. We've also starting to develop tools to help the operators decide what to do. So obviously I've said that in the cab there's no indication of state of charge. Now, even if there was, the driver wouldn't know what to do with that information. Well, they might do after some time, they might get some experience, but in principle, they wouldn't really know what to do with that single number. So in the background, we've got Jonathan's simulation tool and a sort of spreadsheet that says, well, if you need to ask the question to the operator, to ops control, it's basically, okay, where are you? Where are you hoping to go? What's your current state of charge? And then based on the predictions and simulations, it'll give some advice to the operating department and they'll feed that back to the driver via the signaler or whatever. And then the driver can take a decision about what happens next. And one day that might be fully automated, with battery trains, but we're at the early days of that, operational, I don't know, experience, I suppose. But it's just one of the many things we've had to sort of work out as we go along. So we're hoping to build up gradually now. We started to do driver training with Great Western drivers, and we're hoping to get this into passenger service early in the new year, next year, 2025. That will be the real, proof of the pudding, really, because, it's okay doing it Tuesday, Wednesday, Thursday, 6 round trips a day, but doing this 31 round trips 6 days a week is a different game, really. So it'll be interesting to see, how reliable the overall system is. Okay, and just to give you some more figures, this is these are the Thames Valley branch lines, which are run by Great Western. One of the reasons that DFT Great Western picked the Greenford line is exactly because they've got other similar branch lines on their patch. So, one day in future, hopefully we might roll this out to the other branch lines, subject to DFT deciding what to do. But for the Greenford branch, it's about an 8 kilometre round trip. It uses about 40 kilowatt hours, which represents about 9% of the overall capacity of the batteries on the train. Hence, you can get 4 or 5 round trips comfortably. At West Ealing, where it charges, it takes about 3.5 minutes to charge, to essentially to replenish the energy that had been used in the last round trip. So we are charging every round trip, not because we need to, but because it's basically opportunity charging. So you charge it when it's available, and that also stops you discharging the batteries too far as well, which is good for the health of the battery. Sometimes you have to take the train back to Reading, where it's essentially maintained every 18,000 miles. And that's obviously a bit of a longer journey. That's about 50 kilometres. So it wouldn't really get there and back on one charge. So we've got some plug-in chargers at Reading, so that when it gets there, does its maintenance, plug-in charge overnight, and then send it back to West Ealing. The train is normally stabled at West Ealing. There's some sidings there as well, where it's got plug-in chargers as well. So we just plug it in overnight so that it comes out the depot fully charged the next day, hopefully. That's just how we manage it. The question always arises, how far will it go? And it's just, how long is a piece of string? It's like driving your EV. It depends how you drive it. It depends, are you doing motorway speeds or are you doing country lane speeds, which might be the same. But to try and answer this question, Jonathan has done this plot. If you just take the train on a flat route with no passenger load in it and no heating on, and you just ran it, non-stop, it would do about 140 kilometers. So that's not bad. But that's not lifelike. If you then put the heating on in the winter, that reduces the range a bit. If you leave the heating on but slow down and only do 40 miles an hour top speed, then the range goes back up again, and so on and so on and so on. You can see the effect of the different factors, but end of the day, you can't really put a single number on, how far will it go. You have to do the simulations, and it's very much route specific. And we have the longest we've done with the battery train. The furthest we've travelled on one charge. Now, what was it? I think it was 86 miles, because we brought it down from Long Marston in Warwickshire, down the Cotswold line, through Oxford, Reading, through Oxford to Reading, and I think that worked out 86 miles. And that made the press and everything, but it wasn't really representative of what the battery train is doing. Anyway, so it's got plenty of reserve in it, as you can see, and it depends how you treat it. Here's some more stats for you. The system is actually designed for a higher rating. We haven't, for various historical reasons at West Ealing, we haven't had to use the full rating of the system. We're basically limited by, at the moment, we're limited by the traction control unit on the train. There was a decision taken a while ago to use the one we had to save money. The problem with the TCU we have is that it can't handle the power needed for full-on 1,000 amp charging. But the shoe gear and the battery banks and all the rest of it is designed for 1,000 amp current. It just so happens we don't need that at West Ealing. So you could say that we're not actually testing it to its full potential at the moment, and that will have to be something we do further down the line. But there's some stats. I mean, just to pick a few, we charge at about 750 volts, 750 to 815 volts. That's the charge. That's the voltage on the rails. But again, the system is capable of going up to 900 volts on the rails. What else can I tell you? Yeah, you can see table on the left is sort of as designed full rated system. Table on the right is what we're actually doing at West Ealing, and you can just see that the approximate charging time per kilometre. So in other words, if you have the full fat system, after 6 to 12 seconds of charging, 6 to 12 seconds per kilometre, I think that basically means after 12 seconds of charging, you get a kilometre of range, that sort of order of magnitude. But with the current system we're using on the actual train, it takes about 15 to 30 seconds to get a kilometre of range. So you can see that's due to the slightly lower power that we're working at the moment. And yes, just to finish off with some pictures, this is the train running on the Cotswold line, and I think it looks rather nice up in that's Evesham on the left and Morton in Marsh on the right, and a lovely few weeks just going up and down the Cotswold line, accumulating mileage. We took it step by step. So obviously, when we first went out back on the main line, we were over the moon because we'd done all that approval work to get the train back on the main line. But we were a little bit nervous about would it make it to Reading. So we built up gradually. We went out from Long Marston up to Evesham, Morton in Marsh, Evesham, back home again. Yeah, that was about 20 miles or something. And then each day we went a little bit further until we were confident that we could probably make it all the way to Reading. So that was a lovely few weeks, which was back in March and April of this year. One of the things we found in doing that was that driving styles makes quite a big difference to energy consumption. These are histograms showing the power brake handle position. So 0 is no, taking no power, and then you've got 1, 2, 3, 4. That's notch 1, 2, 3, 4 with the power brake controller. So what drivers, the top diagram is what drivers sort of did instinctively. So if you're going lower speeds, they would tend to put in notch 1, notch 2 and just cruise, or just crawl in those sort of speeds. But what we found is that was energizing the motors, and that was leading to losses because they are AC induction motors. So we said, how about try more of a sawtooth driving profile where you put the power on to get up to speed and then just coast, and then put the power on and coast, and that was so the bottom histogram is that where they were doing a lot more coasting, hence the taller 0 column, and that made quite a big difference to energy usage. So the lesson learned there is if we were designing a new train like this, either use permanent magnet motors like they do in EVs, or design your traction control system so that the driver gives a demand and then the TCU sorts it out how best to do it efficiently. Obviously, in our train, it's a bit more old-fashioned and it's very much up to the driver. But you could actually design this in to be automatic to make it more energy efficient. Problem is with a diesel train or over electric train, the driver doesn't really care about how efficiently they're driving. It's more about sticking to the timetable. Well, more so with diesel, obviously you're worried about fuel consumption, but all of a sudden with a battery train, everyone's either worried about the range you're going to do or very competitive about it. We've found the drivers very competitive about energy usage. So, I can go further than you and all that stuff. So this generates its own sort of competition, and we learn a lot from it. So having done testing on the Cotswold line. We finally brought the train down to Reading and then onwards to West Ealing, and then finally running it on the Greenford branch. Nice picture of it there next to the LUL roundel, almost like a homecoming for, well, not that these trains run on the central line, but almost a homecoming for underground train back on the underground system, but as a battery train. Picture in the middle, top middle shows the plug-in charger at West Ealing. Again, nothing really to write home about. It's just that's what it is. Doesn't take up much space. Bottom middle picture was quite amusing because that's a sign at Reading Depot saying no electric traction past this point unless you're a battery train. So that was nice. And then right-hand picture shows the bay platform at West Ealing and with the charging rails in the forefoot. Some more pictures there of various media days and all the rest of it. As I said, we're heading towards full passenger operation. Some might say that we'd taken a while to get there, but actually we didn't want to rush it. We didn't want to suddenly put something into service that then turns out to be terribly unreliable, because we're very conscious that it's an old train. Although it's new technology, it's an old train. So we didn't want to push it too hard. What we don't want to get is a bad reputation for battery technology because of things nothing to do with the batteries. You know what I mean? The fast charging system could be fine, but if we have door faults or I don't know what, you know, wheel flats or whatever it is, we'll probably get a bad reputation, and they'll go, oh, it's a battery train, you know, that batteries are rubbish, all that sort of thing. So we're very, very cautious of not getting a bad reputation, you know, for the wrong reasons. So we're building up gradually. We're going to do more Sunday runs, Sunday full day testing, 31 round trips, and then eventually we're going to start carrying passengers, fingers crossed, in the new year. In the meantime, we're testing it for all kinds of different things, as these nice little images illustrate. So what we've tried to do is define tests that cover all conceivable eventualities of weather, service disruption, component failure. And so, for example, we're coming up to, you know, autumn, leaves, and we're going to, you know, just let the leaves fall on the rails and see what happens. We're not doing anything special, no special maintenance regime to clear them out of the way. We're just going to see what happens when the leaves fall. We've already had oil contamination. We'll hopefully get a bit of snow, perhaps, plenty of rain. One of the things about rain is that it creates, well, if you get wet leaves, for example, building up under the rails, you get earth leakage. Now, the system has got earth leakage detection, such that if it was bad enough, it would shut the system down. But we've already seen that, you know, you can just on a rainy day, you can just start to see you get a little bit of sort of interference in the graphs for earth leakage, and you think, well, just monitor that. But nothing untoward yet has happened. And obviously we've had it running during the summer, so we've tested pretty hot days. This will be the first winter it's done in the actual location, other than the shoe gear testing I showed you earlier. So there's lots and lots of testing that we're doing in amongst the driver training as well. And as I say, gone the wrong way. A lot of that, or most of that, really is about reliability more than anything else. We've kind of covered the safety points now, and now we're into proving this is going to be a reliable system, which so far is looking to be good. Just going to touch on the cost of ownership, because that's another question that sometimes comes up. This slide dates back a few years now. I had a go at trying to estimate the total cost of ownership of doing battery train with fast charging system versus versus other forms of traction. I found in 2019 the EU study called Shift to Rail. They did a study into fuel cells and hydrogen trains, and it's all freely available on the internet. And I took their figures. They broke it down into the cost of train maintenance, the cost of infrastructure, and the cost of the fuel. And then you add those three together to get the total cost of ownership, TCO. And they were looking obviously at fuel cell hydrogen trains versus normal electrification and diesel trains. And I mean, you look at these graphs and it's all pretty self-explanatory. A diesel train costs a bit more to run than a fuel cell train. And an electrified train through the 25 kV is the cheapest of trains to run. We know that. A battery train works out about the same daily operating cost as electric train, as it should, because there's nothing to go wrong really. It's just batteries. There's no moving parts really, other than the motors. So that sort of explains the train maintenance side. The real difference comes in the infrastructure. Now, obviously, we know that electrification is quite expensive. and we can also see that hydrogen refueling infrastructure is also expensive, and having fast charge. Well, okay, you need some infrastructure. You need to pay for the battery banks, trackside battery banks. You need to pay for putting the charge rails in. You need to pay for the DNO connection, which all comes to several £1 million. But the nice thing about installing fast charge is that you can essentially do it in 1 or 2 shifts. So, all we have to do is take a line block, I think, twice to put the charge rails down. Whereas if you're electrifying, you have to, close it for months on end, immunise all your signals and all the rest of it, put your pylon, put your stanchions in, all the rest of it. So, in principle, it's quite a cheap system to deploy. Add all that together, and you can see that actually battery electrification, you can call it electrification by other means, should be quite cost effective. Of course, there are downsides to this. It's a bespoke system, so you have to have rolling stock that is, specifically adapted to this system. You can imagine this wouldn't really be suitable for a large terminus because you'd have to have charge rails everywhere, different lengths of trains. So it really suits branch lines where you've got one type of train, maybe 2 at best, on a fairly standalone basis. Obviously, if you're carrying heavy freight, high speed, you wouldn't use this system. Obviously, you'd use electrification. That's sort of very obvious, really. Well, it is to us engineers, isn't it? Not necessarily to policymakers, but so it's horses for courses. We're not saying this system is the absolute silver bullet for everything. Just being realistic. Now, others have taken it and said, "Oh, this is the future," but they have to be very cautious. You have to be very careful not to get people too excited about it. I don't want to play it down either. We've also done some work on the embedded or embodied carbon of making a battery train. To do this, we looked at the 23001 as a 3-car battery train. We looked at all the material that went into it to turn it into a battery train by mass, essentially. And then there's various online tools you can use to sort of get the average embedded carbon per different type of material. There's also the carbon emitted from running a factory, which things like gas heating, electricity consumption, all that stuff. Even the vans and the cars that VivaRail had, we included that in the calculation as well. And we worked out that this was 2 years ago, but we worked out at that point there was probably about 255 tons of carbon that went into making that battery train, which might sound like a lot. But actually, when you then look at the payback, so you then put your battery train in, take your diesel train out, I think the payback is something like a couple of years, maybe even less. So ultimately, the carbon you burned or carbon you emitted to make the train, you eventually get a saving from withdrawing the diesel train for obvious reasons. So that's just another reason to do this potentially. And finally, we have studied the other branch lines on Great Western and sort of worked out where we might put fast chargers. Whether that happens or not is not my decision, but it can be done, as you can see. There's also scope to do this on other slightly longer routes. You could conceive of using this system, I don't know, on the West Highland line or the Far North line. You might have charging at intermediate stations. You don't have to have it at a terminus. It can be done at intermediate stations along the route. It's quite well suited to where you haven't got ready access to overhead power lines. You might have, say, the 11 kV network. That tends to be what's used in sort of rural areas. You can just sort of plug this into the 11 kV network. So if you've got a very rural station somewhere down in Cornwall or Wales or Scotland, it would be ideal for that. So in summary, it's been very interesting. It continues to be interesting. Hopefully this will, catch on. Somebody will take it and run with it, and whether that's Great Western or somebody else. Yeah, thank you very much.
Thank you very much, David. That was a really fantastic presentation. I really enjoyed it. Hopefully you don't mind if we have time for a bit of question and answers.
Yes.
So who would, just for the benefit of people online, we'll try and repeat the questions, but is there anyone who would like to ask the first question? Chris, you've got your hand up first, so go for it.
When you showed the video of the shoes coming down, so you put down to 10, most third pair of trains, shoes are above the rail level, so you never really worry about that. But clearly, they go below the rail level.
Yeah, they go. Yes, it's essentially so you can clear the so it can run up the ramp and push any contamination off the rail as it does so. I think the actual level of the middle rail is the same as the level of a normal fourth rail. So but we wanted to make sure that the shoe actually clears any contamination as it comes into land, sort of thing. So if you were just coming in and then deploy the shoe onto you might end up compressing any contamination into that patch. So we wanted to wipe it clean, basically. So yeah, a bit of it. And I guess the reason we drop below is just to make sure it has that contact pressure as it comes into land, as I call it.
Okay. If there is anyone online who wants to ask a question, you can put your hand up or put it in the chat, and we'll monitor that. But got another question in the room at the front.
Yeah, on my mobile phone, someone tell me charge it up to 80%, then it dropped to 20% before you charge it again and charge it up to 80%.
Yes.
You seem to be hovering about 75, 85 all the time.
Yeah, for the same reason.
Get a much better life that way than if I did that on my phone.
Oh, that's a good question. Well, one reason we don't fully charge it is because that allows some headroom for regenerative braking as well. So I didn't mention that before, but obviously our train does regen back into the battery. So that gives you the headroom, 20% headroom. But they do recommend that you keep the battery's state of charge between 20 and 80, just like your mobile phone battery. And I don't exactly know why that is. I think it's to do with growth of dendrites or something like that. It's to do with the chemistry. No, ordinarily we don't really. That round trip, I say, is only 4 miles. It only uses that much of the capacity, and because it's thermally managed, it doesn't really matter whether we go down to 20 or not. So if we're running back to depot, it will go down to sort of 40 or 30. We have had it down to 20, which is, but it doesn't really matter because the batteries will shut down when they need to. The thermal management is continuous, so it doesn't really harm the batteries. The truth is, we don't really know until we've run this train for 5, 6, 7 years, 10 years. What we are doing is battery state of health checks every few months, which is to say the battery management system tells you what the state of charge is, but that's as a result of an algorithm that only Hoppica, the battery manufacturer, know what it is. So what we do is we discharge it to a known level, and then we charge it and we measure the volts, amps and time going in, so we actually know exactly how much power we've put into it or how much energy we put into it, and therefore we can see whether there's any divergence between the reported state of charge and the actual state of charge, if you like. And we'll just do that for years and years and years until we have a better picture. One thing my colleague Julian, who's not here, he's sort of become the sort of battery expert within the team, if you like, and he says if you've got the history of the charge cycles of the battery, and you then come to sell your battery to someone else, or you want to try and after a certain lifetime you want to pass it on to someone else, if you've got that cyclic history, your battery is worth more because the battery manufacturer will know the state of health based on that cyclic life of it, and that I think they're developing something called a battery passport, which is basically that life captured in a document or a data file or something like that. And we have so much data from these batteries that we'll be able to show the manufacturer and say, well, what do you think? So it's a bit of a roundabout answer, but hope that helps. Yeah.
They manage to take charge depends on the guarantee the manufacturer will give you. When the leasing company's very interested, so you say, right, you keep that battery for 10 years, then it's a second maintenance cycle, and we'll guarantee that we will maintain 80% of the capacity at year 10. So if you keep it between 20 and 80, it gets you there. If you fast charge and you're going 0 to 100, half your battery life.
Could do, yeah. So yeah, basically work within the manufacturer's recommendation. Yes.
I had a question for you, Dave. That's all right. You had the chart, the sawtooth chart when the Sunday. Did you ever find out why on that at 6 o'clock?
Oh, why
why you didn't get that
Oh, I
full
think
charge?
I think it was a communication failure between the train and the trackside. There was a spike of some sort, and it wasn't happy, so it just stopped charging halfway.
Yeah.
And that happens during testing. I thought actually that for one time in 31 round trips, we were quite pleased with that.
Yeah.
For the first time. But yeah, it just because you've got that extra energy reserve in the train, it doesn't really matter because as you saw, it stepped the graph down a little bit. But it carried on for the rest of the day, and there was plenty enough to get back to the depot. And it would be different on different routes, depending on how far apart or what your round trip distance is between charging, and how much installed capacity you have on the train. But yeah, it was just a blip basically. Nothing serious.
Graham?
You've got the plug-in chargers.
Yes. That's it. Yeah.
Something around a brand of them still plugged in.
Oh, it's all fully in stock. Yeah.
That is a famous thing.
Yes.
Love to take the phone.
Yeah. No. Yes, there's a pin in there that stops you doing that. That was one of the first considerations.
More questions there. Hem at the back.
Yes, that's a good point. You have to be, I can't remember how long it takes to fully recharge, but basically does it overnight. But yeah, if you were deploying the system somewhere else, you'd have to be very, very mindful of how many trains per hour were using it. So again, it comes down to system design. It's not just, the batteries on the train. You're trying to size your trackside battery banks for how many trains are using it per hour or per unit of time. But also, again, allowing a bit of margin for cold weather when the demand might be higher, or hot weather when the demand's higher because of aircon. So you very much have to look at each specific location and do the calculations, make sure you're happy that you've got enough margin for all the trains using it. And of course, with the containers, you can either put more batteries in there, charge them at a higher rate from the national grid, so you can have a higher power connection or more batteries. You can stack the containers too high or have more of them, but it's very much part of the simulations that we can do, is to work that out. So, yeah.
So there was a question. Yeah, do you want to go?
They're definitely faster because they have better acceleration than the diesel units, so despite their extra mass. So the drivers love it, that they end up getting places early. Oh, we're here. But that's not because of the batteries per se. That's because it's electric traction rather than a diesel mechanical drive or diesel hydraulic.
Graham, you had another?
Not a lot. 5 or 6%, I think you get back, if that makes sense. We actually haven't been doing regen up until now. We're going to start doing regen next week, and then we'll actually find out how good it is or not. Right. Yeah. I think I suppose it depends. Well, it depends on how much downhill you've got and how aggressively you brake. So yeah, we'll find out. So I don't know, it won't be massive though. Won't be massive. Well, we don't. Network Rail aren't involved in that. That's an operational decision, but we have an operational decision tool. That's the thing I described earlier. Basically, a spreadsheet where you go, I'm here. I want to go here. I look it up in here. I look up how far it is. Plug in the current state of charge, and then essentially the simulator tells you, yes, that's fine. You'll get there, or not. And if you're not going to get there, then it's time to plug it in and charge it up. So we don't want to get stranded. That would be very embarrassing. And at the moment, because we're all over the train as a team, that doesn't happen. But once it's in passenger service and we're a bit more hands off, those decision tools will come into their own, and we're training the ops people within Great Western to use these tools. We're going to do a bit of a dress rehearsal in a few weeks' time of pretend that we're not there and say the driver's in the depot wanting to go from West Ealing to Reading. Driver has to phone up ops control and say, right, I want to go. Is it basically yes or no? Can I proceed? We're trying to do it in a way that's not too onerous, because what you don't want to be doing is phoning the signaller all the time. So if we don't involve the signaller, they've got enough work to do already on the Great Western Main Line. It's all within Great Western, that decision. But even if we did run out of charge, there's ways of rescuing the train. It's just embarrassing.
Do you think if Adrian hadn't pushed you to try and get that third battery bank onto the
on the
train,
train? Well, yeah, all that actually would mean is that we couldn't have done so many round trips without charging.
Yeah.
when we all the simulations we've looked at other lines, and when we're doing simulations, what we're trying to do is size the trackside battery banks. It sort of goes back to your question. We size the trackside battery banks to make sure that and the charging system overall, to make sure it replenishes the energy used in a given round trip. The actual batteries on the train are all you actually need is enough capacity to get from A to B. You see what I mean? So, but we just happen to have a lot of battery on our train, which is great because it means we've got more resilience. So think of the capacity on the train as your resilience. All you actually need is enough for one round trip if you've got the charging system right. But in reality, all manufacturers are going to put more than they need onto their train, because you just don't know what's going to happen out there on the real railway. So,
one more question.
Yeah, the plug-in train stopped in the right side when it comes to station. It is down the driver looking at markable.
Yeah, just a markable. Yeah, just training mostly. Yeah, I mean, one or two. We've had a couple of overshoots where not where they've hit the buffers, but where they've stopped a bit too far beyond. And you go, oh, why isn't it charging? Oh, because they've gone too far. But they'll get used. They have got used to it, and they are getting used to it. Oh, you certainly could. I mean, we won't do it with this trial, but if any battery train manufacturer would probably be looking at that sort of thing. Yeah, it would make perfect sense.
In the meeting chat, there's no questions. Online audience. If we have one more from the room.
Okay, so on the other Thames Valley branch lines, 230 or something else?
I would say 230s are perfect. We should do some more 230s. I think they would be absolutely perfectly suitable, and it would be quite easy to roll out in my view. But others, without saying too much, there's other ideas within Great Western for standardising rolling stock. There's a thing called Project Churchwood, which is about the long-term needs of rolling stock on Great Western. But a lot of it comes down to what happens with GWR and etc. etc. So there's lots of cars left. Yes, I think there's something like 80 something cars left. There might be a bit fewer now, but I think it worked out we can probably do about another 14 Class 230s on the basis of having enough driving motor cars to do that. So there's plenty enough to do Thames Valley. Yeah.
That's fantastic. And the presentation today was really good. Certainly showed us a great history of the Class 230 and a bit of a dive into some of the technical details as well, which as engineers, I'm sure we all enjoyed to see some of those stats and bring it to life with some pictures and videos. It really was a really good presentation. So thank you, David, very much for coming and delivering your presentation today. We could all thank David in the usual way, please. Okay, well, that wraps things up for tonight. We'll be back with our next presentation, which is on the Central Line Improvement Programme, which is being reorganised from last year, and that will be on the 16th of October. Again, there's options to be in person here at RSSB or online. So thank you very much, everyone, for joining. And looks like there's one message from Graham before we finish.
Just to emphasise that the chairman's address is being covered one day.
Okay. 26th of September, one birdcage walk to see Ian Ray who is the current Railway Division Chair. He'll be giving his Chair's address. So if I don't see you there on the 26th, hopefully see you back here on the 16th of October. Thank you very much. Stop recording.
Thank you.
Oh, and yes, we're going to go to the Red Lion pub. If anyone would like to join us, that would be fantastic.
Cool. Yeah.